So you want to build a continental power grid. You start by looking out over the quiet, harsh sands of the Gobi Desert in Xinjiang. You decide to build a huge sea of millions of solar panels that stretch to the horizon. Beside them, you erect a giant steel power tower over 100 meters tall. This large structure must hold up a set of thick, heavy metal power cables. Shoot these high-voltage lines eastward across thousands of miles of rough mountains, cross deep river gorges, and run straight into the bright skyscrapers of Shanghai. But moving large amounts of electricity across an entire continent breaks a basic rule of physics. Under normal grids, your power will simply burn off into the air as heat. To get around this problem, you must build a network running at 1.1 million volts. This is how you build the most extreme electrical highway on Earth. Before building, though, you have a distance problem. You face a huge geographic power problem. Most clean energy is stuck far in the west, where giant wind and solar farms sit in empty deserts. But your massive factories are located on the coast, and cities like Shanghai need huge amounts of power every day. This creates a massive 4,000-kilometer distance gap. Sending electricity this far triggers a harsh physics rule known as Joule heating, where energy loss equals current squared times wire resistance. Resistance naturally grows as your power cable gets longer, and long wires act like giant heaters, bleeding electricity away. Standard power lines fail completely after 500 kilometers. Alternating current gets blocked by three major problems. First, magnetic drag drops your total power capacity. Second, long lines cause dangerous voltage spikes that can easily damage critical grid insulation. Third, current suffers from the skin effect problem, where electricity only travels on the outside of the wire and leaves the center of your cable completely unused. This uneven flow wastes a large amount of energy, and your standard grid would lose most of its power. To save your cities, you have to work around physics. You solve this problem by changing the electricity type and giving up standard alternating current completely. Instead, you choose ultra-high voltage direct current, and your biggest success is the Changji-Guquan power link. Run this system on smooth, steady direct current, and because direct current has no wave cycle, problems disappear. The dangerous skin effect and voltage spikes simply go away. The key behind your system relies on basic math, where total power equals voltage multiplied by current. Pushing the voltage up to 1100 kilovolts lowers the current, and this matters because line heat grows with current squared. Cutting the current down keeps your wire from melting, and this large voltage increase reduces line losses by 80%. Now, power travels safely across 3,000 kilometers, and your line can carry 12,000 megawatts of energy. That equals the energy output of 12 nuclear plants. To handle this massive load, always use special cables where each power line splits into 8 separate aluminum wires. Hang the wires in a wide, even circular pattern that spreads out the space around the cable and keeps the strong electric field tightly under control. This trick stops the electricity from tearing the air apart and completely prevents dangerous sparks and loud hissing sounds. Special carbon fiber cores inside keep the lines perfectly straight, and your highway stays steady even under harsh weather conditions. The biggest danger of 1100 kilovolts is an uncontrolled spark, and at this level, electricity can literally jump right through open air. It pulls electrons from air molecules, creating a violent arc flash that produces temperatures hotter than the surface of the sun. To contain this danger, your substations must seal equipment inside metal tubes that are filled with pressurized sulfur hexafluoride gas. This gas molecule easily attracts and catches free electrons, and it quickly grabs stray electrons to put out dangerous electrical sparks. This trick lets your substations shrink their footprint by 80%. Inside large concrete halls, place multi-story thyristor valve towers that act as massive, fast solid-state switches, and they constantly convert alternating current into smooth, direct current. To stay cool under heavy loads, make them use purified water loops. Moving power out of the halls needs special wall bushings, and these large insulated tubes measure over 11 meters in length, with each heavy bushing having a mass of roughly 6 tons. The transformers at these stations are among the largest on Earth. Every single unit weighs a huge 800 metric tons. They are 32 meters long, and they need custom train cars. Because they are too heavy for mountain roads, you must build them on-site and fill them with refined synthetic oil for insulation and cooling. This massive network carries a dangerous hidden weakness that you must call the strong DC, weak AC coupling trap. Your receiving grid must stay perfectly stable to accept power, and the conversion process relies on a precise timing angle known as the thyristor extinction angle. If a simple short circuit happens on your coastal grid, the local alternating current voltage will instantly drop. This drop shrinks the timing window inside the switch, and your heavy electrical switches fail to turn off in time. This mistake causes a serious commutation failure, where your line's direct current voltage collapses instantly and the current spikes sharply. This freeze completely stops all cross-country power flow. In busy industrial areas, multiple lines end together, and a single small short circuit can cause a chain reaction where multiple massive grid highways fail at the exact same moment. Your grid can lose 30,000 megawatts in milliseconds, and this sudden loss can set off a massive cascading blackout. To prevent this nightmare, you must install large protective machines and use specialized 300 megavar synchronous condensers. These are large spinning machines with no mechanical load, and their spinning mass stores a large amount of kinetic energy. During a fault, make them instantly push reactive current into the grid to support local voltage and stop the failure chain. You must also use advanced voltage source converters that rely on high-capacity press pack (IGBT) transistors. The tiny switches are stacked tightly under heavy spring pressure and adjust power in less than 10 milliseconds to protect the grid. But your highway faces another threat up in the sky, where freezing winter storms create heavy ice buildup on cables. Cold desert winds turn the frozen wires into wings, and this lift effect causes a problem called conductor galloping, where the heavy cables violently jump up to 12 meters vertically. This intense bouncing can easily snap steel towers like twigs, so you must install special anti-galloping dampers that absorb wind energy to keep the continent highway safe. Now that the hardware is in place, it's time to plan the grid. Span this cross-country power highway across 5 Chinese provinces and begin your journey deep inside the deserts of Xinjiang. Connect your large Changji sending station to local power grids, and from there, route the heavy cables through Gansu province to cross the narrow valleys of the Hexi wind corridor. Next, make lines collect solar energy across Ningxia before reaching the difficult heights of Shanxi province. The highway must climb straight over the Xinling Mountains, and this tough terrain requires strong steel tower designs. After crossing Henan, terminate the lines at the Guquan station in Anhui province. Pushing 12,000 megawatts into one spot is dangerous, as it can easily overload local city power networks on arrival. To fix this, always use a layered connection setup where half the power connects to the 500 kilovolt network and the other half joins the 1000 kilovolt system. This split protects the local eastern grid from overloading. But the Yangtze River presents one last physical barrier, and building large overhead towers inside the wide river is impossible. because it would badly block international shipping traffic below. Instead, you dig a special utility tunnel under the riverbed called the 5.5-kilometer Sutong Pipe Gallery, which runs deep underground between Nantong and Suzhou. The lines are sealed inside tubes filled with sulfur hexafluoride, and this underground highway moves bulk energy safely beneath the water. By the end of 2025, you aim for an incredible grid size, finishing 46 working ultra-high voltage corridors that stretch over 62,000 linear kilometers. These massive lines must handle most of your cross-provincial power capacity. In early 2026, you adopt an even bigger plan and launch a massive 4 trillion yuan capital spending budget that equals over 550 billion US dollars. This funding runs under the new 15th five-year plan, and the goal is to build 15 brand new corridors by 2030 to support massive desert clean energy bases. But adding wind and solar power brings a final problem, because renewable energy is naturally unpredictable and unsteady. Clouds block the sun and winds suddenly stop blowing. So to keep the long continent highway perfectly stable and steady, you must build large coal power plants next to solar fields. Make fossil fuel plants act as a permanent backup power source, and this trade-off keeps the electricity stream flowing without stopping. Your 1100 kilovolt grid is not just simple power wiring, and it works as a planet-scale civil engineering achievement. Your system will completely change how you move energy, and by crossing thousands of miles, you will beat severe resistance losses. Now connect remote desert winds directly to busy coastal cities, but this success requires an enormous ongoing financial commitment. Your 4 trillion yuan expansion shows the grid will keep growing, and 15 new ultra-high voltage highways will soon cross the country. Keep them tied to a permanent engineering compromise with coal, yet the massive cross-country energy network is completely solid. The old physical limits of distance have finally been broken. You have successfully built a unified, continent-spanning power system, and the rules of global infrastructure are changed forever. If you want to support the channel and learn more about modern China, then remember to subscribe. See you in the next video.